Have you ever stopped, maybe while your washing machine's going, and just wondered, how does it do that? How does it spin? Or, your blender, what's making it whir?
It's funny, isn't it? We're surrounded by these things, these movements, but we rarely think about the invisible forces behind them.
Exactly. It feels like magic sometimes, but it's not. It's physics. And that's what we're diving into today, this really cool link between electricity and magnetism.
Specifically, how that link makes things move.
Right. We're going to unpack something called Fleming's left-hand rule. Sounds a bit technical, maybe, but our mission here is to break it down, make it super clear.
Yeah, we want that aha moment for you, where you suddenly see how all this tech around you actually works.
And we're drawing inspiration from Jun Byung-chul's book, Jeonpyeong,
which charmingly translates to something like True Beginner's First Steps in Electricity. So, the whole approach is designed to be really accessible, no prior genius needed.
Definitely not. Okay, so let's start at the beginning. The absolute core idea is this. When electricity, electric current, flows through a wire, it doesn't just travel along the wire, it actually creates something around the wire, an invisible magnetic field.
Right, like ripples spreading out from the current.
Yeah.
You can't see it, but it's there. And that discovery, that connection, that was huge.
Huge, because it let us create electromagnets.
Exactly. Suddenly we had magnets we could switch on and off, control, increase the power, decrease it, reverse it even. All just by changing the electricity.
That control is key.
Totally. It opened the door to doing, tremendous things.
And maybe the biggest tremendous thing based on this is the electric motor.
The
Aishan.
Yes, the motor. Fundamentally, it's just a machine that takes electrical energy.
And turns it into spinning energy, rotational movement.
Precisely. Electrical in, mechanical out. Simple concept, but wow, it changed everything. Our whole modern world runs on motors.
No kidding. Think about it. Your vacuum cleaner?
Yep.
Washing machine, obviously. Refrigerator. Does that have one?
Oh, yeah. It's got compressors and fans, all driven by motors, blenders, air conditioners, electric fans.
Mixers, hair dryers.
The list just goes on and on. They're absolutely everywhere. The hidden heartbeat, you could say.
That's a good way to put it. And the source mentions there are different types too, right, depending on the electricity.
Right. Broadly, you've got DC motors, tunyo, for direct current, like from batteries.
Yeah.
And then induction motors, which run on the alternating current, AC, from your wall sockets.
Okay, so different flavors for different jobs. We don't need to get bogged down in the details of how they differ right now, maybe.
No, not essential for the main idea. The core principle is the same. Electricity plus magnetism equals motion. The big question was always, okay, we know it moves, but which way?
Right. If you're designing something, you need to know if it's going to spin clockwise or counterclockwise or move up or down. How do you predict that? Especially with invisible forces.
Exactly. Imagine being one of the early engineers trying to figure this out. You've got a wire, you put it near a magnet, you run current through it. It jumps. But which way will it jump next time?
You'd need a reliable way to know.
And that's where J.A. Fleming came in with his stroke of, genius. But simple genius. He gave us Fleming's left-hand rule.
Not some crazy equation, but a hand gesture.
Basically, yeah, a visual mnemonic,
Yeah.
a way to use your own hand to figure out the direction of that force. It made something abstract feel really concrete.
Okay, I'm intrigued. Let's try it. You listening can do this too. Hold up your left hand.
Yep, your left hand. Now you need to arrange your thumb, your first finger, index finger, and your middle finger. So they're all at right angles to each other, like 90 degrees. Your index finger points forward, your middle finger points out to the side, and your thumb points straight up, all perpendicular.
Okay, got it. Looks a bit like a coordinate system. X, Y, Z axis, kind of.
That's a great way to think about it. Each finger represents one key part of the puzzle.
Right, so what's what?
Your index finger, the first finger that points in the direction of the magnetic field. Remember, magnetic fields have a direction, usually shown as lines going from North Pole to South Pole.
Okay, index finger, field direction.
Got it. Then your middle finger, that points in the direction the electric current is flowing through the wire.
Middle finger, current direction.
Okay, and now the magic part. Your thumb. Whichever way your thumb is pointing, that's the direction the force will push the wire. That's the direction of motion.
Whoa. Okay, so field, current, force, FBI almost, but with the middle finger for I, current.
Some people use that, FBI. Thumb is force, index is field, B is the symbol for magnetic field strength, middle is current, I is the symbol for current. Whatever helps you remember.
That's actually really helpful. FBI, Thumb, index, middle. Okay, so let's take the book's example. It said, if the current moves from right to left.
Right, so you point your middle finger current to the left.
Okay, middle finger left. Now, depending on the magnetic field direction, index finger, let's say the field is going into the page, away from you.
Then your index finger points forward. Now, to keep those fingers at right angles, you might have to twist your wrist a bit.
Yeah, okay, doing that. And my thumb is pointing downwards.
Exactly. So the rule predicts the wire will be pushed downwards. It gives you the direction of the force. Simple, visual, effective.
That's genuinely cool. And why the left hand specifically?
Ah, good question. The left hand is traditionally used for motors because we're starting with electricity, current, and
Yeah.
a magnetic field, and we want to find the resulting motion or force. Input is electricity, output is motion,
Okay, that makes sense. Left hand, motor action, electricity to motion.
which naturally leads you to wonder,
Yeah,
is there a right-hand rule?
I was just thinking that.
And yes, there is. Fleming figured out both. The right-hand rule is essentially the flip side of the coin. It's for generators.
Generators, they do the opposite, right? They make electricity.
Precisely. With a generator, you start with motion. You physically move a wire through a magnetic field.
And that movement creates an electric current.
Exactly. It induces a current. So with the right-hand rule, your thumb points in the direction of the motion, the force you're applying. Your index finger still points in the direction of the magnetic field.
And the middle finger then shows the direction of the current that gets generated.
You got it. Same three elements: field, motion, current, current. But the cause and effect are swapped. Left hand for motors, current in, motion out. Right hand for generators, motion in, current out.
That duality is fascinating. The same physics working in reverse. But wait, the source said something even more surprising, that some motors can be generators.
Yeah, isn't that neat? Many simple DC motors exhibit this property perfectly.
So the same device.
Yep. Put electricity into it, it spins, it's a motor. But if you take that same device and you spin its shaft manually,
It produces electricity.
it generates a current.
Yeah.
It acts as a generator. The parts inside, the coils and magnets are the same. It just depends on whether you're putting electricity in or taking it out.
That sounds like something out of science fiction, but it's real.
Very real.
Yeah.
And incredibly useful. Think about modern electric cars.
Okay. How does it apply there?
Well, when you accelerate, the battery sends power to the motor.
Yeah.
It spins the wheels. That's motor mode, standard stuff.
Right.
But what happens when you lift off the accelerator or you brake? The wheels are still turning, right? They're making the motor spin.
Ah. So the car's momentum is now spinning the motor.
Exactly. And in that instant, the motor switches roles. It becomes a generator.
And it generates electricity. Where does that go?
Back into the battery. It's called regenerative braking. Instead of wasting that kinetic energy as heat in normal brakes, you recapture some of it as electrical energy to recharge the battery a bit.
Wow. So the motor is also helping to recharge the battery while slowing the car down.
That's the idea. It's a brilliant piece of engineering, exploiting that very motor-generator duality we were talking about.
Mhm.
Makes electric cars much more efficient.
That's a fantastic real-world example. It really brings it home. So when we tie all this together, what's the big takeaway for you listening?
I think it's realizing that these seemingly simple rules, these basic interactions between electricity and magnetism, they're just dusty textbook concepts.
Right. They're the absolute foundation for so much technology we rely on every single day.
Yeah, from your toothbrush to cutting-edge electric vehicles. And understanding Fleming's rules, even just the basics we've discussed, it's like getting a decoder ring for the modern world.
It definitely makes things less mysterious. You push a button, something spins, now you have a much better idea of why. It's not magic, it's just elegant physics applied cleverly.
And it hopefully makes you appreciate the ingenuity behind even the simplest appliances. It's about understanding things quickly but properly without feeling totally lost in the jargon.
Taking those first steps, like the book title says.
Exactly. Seeing the amazing complexity hidden in everyday objects.
So here's something to think about now that you got the basics of Fleming's rules. Where else might these principles be at play? Are there other hidden motors or generators around you?
Maybe in unexpected places like those hand crank emergency radios or flashlight.
Oh, good one. You crank it, motion, it generates power, current, using the right-hand rule principle. What about tiny fans and computers? Or, what new things could we invent just by tweaking these forces?
The possibilities are kind of endless once you grasp the fundamentals. Maybe you'll look at a spinning toy or a kitchen gadget differently now.
Hopefully. Well, thank you for joining us on this deep dive into the world of motors, magnetism, and Fleming's handy rules.
Yeah, it's been fun exploring these foundational ideas.
We hope you look at the whirring and spinning things in your life with a bit more curiosity now. Maybe even try the hand rule yourself. Until next time, keep questioning.